Hello everyone, welcome back. So in today's video, we're going to solve few problems from paper 2 of JEE Advanced 2024. Okay, so this is problem number 1 and this question was from the topic of motional EMF. We have a region in the form of an equilateral triangle in the xy plane of height L and uniform magnetic field B pointing in the plus Z direction. So the x-axis is in the downward direction, y-axis is in the horizontal direction, and z-axis is again coming out of the page. So the magnetic field is only present in this triangular region. It's given that at time t equal to 0, the loop starts entering the region of the magnetic field with a uniform velocity of v in the plus x direction. So the plane of the loop and its orientation remains unchanged throughout its motion. So we have to figure out the variation of the induced EMF in the loop as a function of the distance. Okay, so we have to plot the E versus X curve. From the diagram, we can see that at time t equal to 0, the tip of our loop is at point P or X equals 0. Okay guys, so initially at time t equal to 0, this was the configuration of the system and the horizontal axis also coincides with x equals 0. Okay, so let's say after some time, the loop actually moved down by a distance of x. So as you can see, the tip actually moved down by a distance of x. Okay, so now before moving on to the general solution guys, there is a really easy way to solve this problem. Okay, so let's just discuss the easy solution first, then we'll discuss the geometrical solution. So the induced EMF in the loop, we can figure out using Faraday's law. It is minus d phi by dt. Right, so but I can kind of modify this derivative and write it as d phi over dx times dx by dt. So this just means the same thing, or what you can do is write it as d phi by dt itself, but in a time of dt we know that the triangular loop moves down by a distance of dx by v, right? So instead of dt you can write it as dx divided by v. So basically you can also write it this way. Alright, so now in the options, if you observe, we have been given E versus X plots, right? And now we have a relation on E and X. So if I take dx to the other side and let's say if I integrate on both sides, then on the LHS what I obtain is the area under the EX curve, and the RHS just simplifies as minus V times delta phi. So now the interesting idea is that in the initial situation when the loop was completely outside, the flux through our loop is 0, right? So the initial flux would be 0. Now after covering a distance of L, it will reach this configuration, and after covering another distance of L, it would reach this configuration. This was at x equals 0, and when it covers a distance of x equals 2L, the flux again becomes 0. So now if I observe between x equals 0 and x equals 2L, the change in flux is going to be 0. My area under the EX curve should turn out to be 0 if I consider the x values from 0 to 2L. So now if you observe the options, option C definitely cannot be the answer because the area is negative. Here the positive area is greater than the negative area, so D cannot be the answer as well. Again, B cannot be the answer. And so the only option that has the potential to be an answer is option A. So this was the easiest way to solve this problem, you could say. So now let's talk about the geometrical way to solve this. Okay, so the idea of the geometrical method is again very simple. All we have to figure out is d phi by dx, right? Now if we just observe the motion of the loop, then from x equals 0 guys till x equals L, as you guys can see, it is going to, the common region is going to be a diamond basically, right? But once it crosses x equals L region, it becomes a hexagon, right? So the function of the area actually changes from x equals L to x equals 2L. So first we have to analyze from x equals 0 to x equals L. So for x lying between 0 and L, okay, so first we have to find the area of this common region. So if I draw a horizontal here, again guys, this angle is 60 degree, right? Because it's an equilateral triangle, so this angle will be 60. So if I have an equilateral triangle whose height is given to be h, let's try to figure out its area. So this angle is 30 degrees. So the base length is going to be 2h tan 30. So the area of the triangle is going to be half height times the base, or simply it's going to be h squared times tan of 30. So we are going to be seeing a lot of equilateral triangles, so we'll just use this result directly. Now the total height of the diamond is actually x, right? So the height of the equilateral triangle is going to be x by 2. So the total area is going to be twice of x by 2 squared tan 30. Okay, this is the area of one triangle and we multiply it with 2 to get the total area. So this turns out to be x squared by 2 root 3. Okay, so the area as a function of x for all x lying between 0 and L is this particular function. Okay, so now let's talk about the situation for x greater than L guys. From the initial point, the tip of the triangle has traveled a distance of x. Okay, so now the height of this triangle is again capital L guys. So the height of this very small triangle over here is going to be L minus x. So as we know the height of this triangle, we can figure out its area. Now guys, this angle is 60 degree. Now guys, all these triangles that you see on your screen are equilateral triangles. Why are they equilateral triangles? It's pretty easy to see. So this triangle is equilateral clearly, right? Because the base is parallel to the base of the bigger triangle. So this angle will be 60. So which means this angle should be 60 as well. This angle is anyway 60. So which means this angle will be 60 as well. So if this angle is an equilateral triangle, by symmetry even this angle is equilateral triangle. And you can use the same arguments to prove that even these two triangles are equilateral. Okay guys, so this should be x minus L, not L by L minus x. So even this length is going to be x minus L guys, because this height is also L. So which means this is x minus L. Okay guys, so now this black length over here is going to be 2L minus x. Okay, so basically if you add both of these lengths together, you should get L. Okay, so now easily we can see that guys, this is a very symmetrical structure, right? So these two lengths will actually be equal, which means the length of this triangle is going to be half of 2L minus x, which is L minus x by 2. Okay, so the height of all these four triangles are the same and it is equal to L minus x by 2. So now we can easily find out the area of all the triangles. So the flux will only be passing through this region, right? The hexagon in middle. So what we can do is from the big yellow triangle, we can subtract this yellow triangle, this yellow triangle, and the third this yellow triangle. Then I will get the hexagonal region in between. So the area of the bigger triangle is going to be L square tan 30, and from that we'll subtract the area of this top triangle is x minus L whole square tan 30, and we have two triangles whose height is L minus x by 2. So this will be 2 times L minus x by 2 whole square times tan 30. So this is the area as a function of x for x greater than L. Okay guys, so earlier we figured out that the EMF was minus V times d phi over dx. Magnetic flux, I'm going to write it as B into A. So it will be minus BV times dA by dx. So we figured out area as a function of x. So now all we have to do is figure out dA by dx. So after differentiating, it turns out to be this piecewise defined function. The thing is guys, if you put x equals L here, you'll get the answer as L by root 3. And if you put x equals L here, in this function, here also you'll get L by root 3. Means the curve is going to be continuous at x equals L. Okay, so now the EMF is nothing but just minus BV multiplied to this function, and you'll get this as the EMF. Okay, so now let's try to plot it. So the EMF from 0 to L, it is a straight line with a slope of minus BV by root 3. Okay, so this is still x equals L. And after x equals L, what happens is we have a straight line with a positive slope. And if you observe, the slope is 3 BV by root 3, which is actually 3 times the slope of the first line, right? So the second line will be more vertical than the first line, and it will look something like this. And this will happen till x equals 2L, and after x equals 2L, obviously the EMF will be 0. So this is the curve for EMF versus x. You can also figure out where it becomes 0. All you have to do is equate this term to 0, and this point will turn out to be x equals 4L by 3. Okay, so that was it for this question guys. So now let's move on to the next question. Okay guys, so this is again a problem from gravitation and central force motion. There was a problem from central force motion in the first paper as well. So here we have a particle of mass m that is under the influence of a gravitational field of a body of mass capital M. The mass of capital M is given to be orders of magnitude greater than small m. So the particle is moving in a circular orbit of radius r0 with a time period of t0 around the mass m. So the situation is pretty simple. We can assume the capital M mass to be some planet, and then we have a very small mass in comparison to the planet, which is in an orbit of radius r0, and the orbit is circular in nature. So the velocity is perpendicular to the radius. So this is the situation given to us, and it's given that the time period of its oscillation is t0. Now it's given that the particle is subjected to an additional central force corresponding to the potential energy of m alpha divided by r cube. Alpha is a positive constant. If the particle moves in the same circular orbit of radius r0 in combined gravitational potential due to capital M and Vc, then we have to find the new time period of t1. Okay, so now the potential function of central force is given. So V is given to be m alpha divided by r cubed. The central force we can obtain by finding the negative gradient of the potential. Now as the potential is just a function of r, F just becomes minus dV by dr. So now if we differentiate the potential function, it will turn out to be minus 3m alpha divided by r power 4, and the minus and minus just cancel each other out, and this becomes 3m alpha divided by r power 4 in the r cap direction. So if you observe, the central force is not towards the center, but it is away from the center. So the central force in this case turns out to be in the plus r cap direction and not in the minus r cap direction. Okay, so now all we have to do is write F equals ma in the radial direction for this small sphere. So firstly we have the gravitational force, which is G capital M small m divided by R0 squared, and then we have the central force, which is towards the right, which is opposite to the gravitational force whose magnitude is minus 3m alpha divided by r naught to the power 4, and this would be equal to the mass of the small mass times the centripetal acceleration. Now guys, the centripetal acceleration we can write it as omega square r, but omega we can write it as 2 pi by time period, right? Because this is uniform circular motion. So this will be m r naught 4 pi square divided by t1 squared. So this is equation number 1. So now in the first case guys, the only difference is that the central force is 0, right? So we can just say G capital M small m divided by r naught squared equals m r naught 4 pi square divided by t naught squared. So now if I just divide both of these terms, now I'll get a ratio for t1 and t naught. So once I divide both of these equations, this is the expression that I get. So now I'm going to take this term to the other left side and this term to the right side. So what I obtain is t1 square minus t naught square divided by t1 square on the left side, and on the right side it becomes 3 alpha upon gmr naught squared, and that corresponds to option A. So now let's move to the next question. So problem 3 is from X-rays. So this question is quite straightforward if you know the basic definitions, guys. So let's read the problem first. So we have a metal with an atomic number of 46. It is given that it is bombarded with high energy electron beam. So this is basically what Moseley's experiment was. The emission of X-rays from the target is actually analyzed, and they've given us a ratio small r, which is the ratio of the wavelength of the K alpha line and the cutoff. Okay, so we'll briefly discuss what those are. And the first case, it is found to be 2. Now it's given that the same electron beam bombards another metal target with atomic number of 41, then what will be the value of R? So in this situation, guys, what happens is we fire high energy electrons at a metal target. So let's say this is the atom of the metal and this is the K shell. So here there are 2 electrons, one s1 and one s2, and then this is the L subshell and this is the M subshell. Okay, so there could be a lot of possibilities that happen in this case. One possibility is that the electron crosses the atom of the particle. It leaves with some kinetic energy K dash, which is less than the initial kinetic energy. And how did it lose the energy? Because of collisions with other electrons, right? And the decrease in this energy is emitted as photons in the X-ray region. So that is one possibility. The situation in which all of the energy of the incident electron gets converted into the energy of the photon is what we call as the cutoff case. Now guys, these electrons are first of all accelerated across a potential, let's say V naught. So the initial kinetic energy of the electron is, let's say, EV naught. So if the entirety of this energy EV naught is converted into the energy of the photon, which is hc by lambda naught, so this lambda naught is what we call as the cutoff wavelength. And if you observe something, the cutoff wavelength has nothing to do with the metal target. It is basically dependent on the potential difference across which the electrons were accelerated, or basically the initial energy of the electron beam. It's given in the problem that even in the second case, the electron beam has the same energy. So which means the cutoff wavelength remains unchanged. It's going to be the same in the second case as well. Now there is also one certain possibility, guys, in which the electron collides elastically with the electron present at the K subshell and it knocks out the electron present in the K shell. So now what will happen is there would be a vacancy over here, right? And in order to fulfill that vacancy, the electron from the L subshell will come to the K subshell. And this is what we call as the K alpha emission. From here, as you can see from this diagram, the transition of electron from n equals 2, which is the L shell, to n equals 1 is what we call as the K alpha emission. And if it's from n equal to 3 to n equals 1, it is going to be K beta, and so on and so forth. So now when the electron from state 2 comes to state 1 to fill the vacancy, the energy lost by the electron is emitted in the form of a photon, similar to what we learned in the hydrogen spectrum. So basically energy of state 2 minus energy of state 1, or we can also say it is a EL minus EK. So let's say this is equal to delta E. So now the energy of the photon is going to be delta E. So this we can say it is equal to hc divided by lambda K alpha. So this is the wavelength of the X-ray emitted due to K alpha transition. Now how do we figure out EL minus EK? For this, guys, you guys may be familiar with Moseley's law. We can actually use the same formula that we use for hydrogen spectrum, but here there is a slight modification in the formula. So now for the hydrogen spectrum, it was RHC. The delta E was RHC times 1 by N1 squared minus 1 by N2 squared, right? There would be a Z square as well. And this RHC is nothing but 13.6 electron volts, guys. Now for K alpha transitions, we can say the change in energy is same RHC, but here instead of Z, we are going to write Z minus 1. And the reason that we are doing this has to do with the shielding effect of electrons. So basically observe the electron in the L subshell. When the electron looks towards the nucleus, what it feels is the total charge of Ze and minus E. So that is like Z minus 1 times E, right? So in the hydrogen spectrum, the net charge that it feels is ZE, right? There's only one electron in the orbit. So, and that's the reason why we use Z minus 1 here. Now this is not an exact formula, guys, but this is a very good approximation. Okay. So now as we are talking about K alpha transition, we'll set N1 equals 1 and N2 equals 4, and we'll also equate delta E to Hc divided by lambda K alpha. The wavelength of the K alpha X-ray turns out to be 4 divided by 3r times z minus 1 the whole squared. So basically r2 by r1, what they asked in the question, is nothing but lambda K alpha 2 divided by lambda K alpha 1, right? Because the cutoff wavelength, as we discussed earlier, remains the same. So this is going to be z1 minus 1 the whole square divided by z2 minus 1 the whole squared. Now r1 was equal to 2, so we'll multiply this with 2 as well. And once you solve this turns out to be 2.531, and that matches with option A. Okay, so now let's move on to the next question. Okay guys, so in this question we have a thin stiff insulated metal wire that is bent into a circular loop with its two ends extending tangentially from the same point. The loop has a mass of small m and a radius of small r, and it is in a uniform vertical magnetic field B naught as shown in the figure. So the magnetic field is in the y cap direction. Initially it hangs vertically downwards because of acceleration due to gravity G, okay, on two conducting supports at P and Q. So now it's given that a current I is passed through the loop. So obviously there will be some torque due to the magnetic field acting on this loop, and hence as a result the loop is going to turn, and they are saying the loop turns about the line PQ by some angle theta. And this is exactly what the problem with the question is. They're not clear with what they're asking, right? They're just saying it turns by an angle theta. So let's just start discussing this problem. So let's say the current I is flowing towards the right. So in the loop it is flowing in the clockwise sense. So now let's look along this direction and observe the situation. Okay guys, so let's say this is the point Q, and this straight line that I drew is the ring. Now guys, if you curl your fingers in the direction of current, you'll get the direction of the magnetic moment vector, and it will turn out to be right as viewed from this direction. Now guys, the magnetic field is in the vertically upward direction. So if you do M cross B guys, the direction turns out to be out of the page. Now guys, this M cross B torque is the same about any axis, and the reason for that is because the torque is actually a coupled torque. So basically even the torque about the horizontal axis passing through Q is going to be M cross B. So now as the torque is out of the page, the direction in which the ring will rotate is in the counterclockwise direction. And this torque is going to be a variable torque guys. Why? Because the M vector is changing with time, right? But the issue here is that this will never come to equilibrium unless and until there is friction in these two rails. So unless and until there is some damping agents, this ring will never come to equilibrium, or it will never come to rest. So basically what will happen is the magnetic torque will try to rotate it in the counterclockwise, and the gravity torque will try to rotate it in the clockwise direction, and there will be a point somewhere in between where both of these torques are equal, right? And this is where the equilibrium condition is, okay? But the thing is, at this point the omega of the ring will be maximum, and it will further continue moving till it comes to rest, okay? And this angle, if you guys are familiar with it, is twice the equilibrium angle. So let's try to figure out both the angles, okay, and let's see what happens. So first let's talk about the equilibrium angle. Okay guys, so first let's talk about the equilibrium angle. Let's say the angle is actually theta. So this is the point where the magnetic torque and the gravity's torque actually balances each other out. Now here the M vector will be in this direction, right, perpendicular to the plane of the ring, and the magnetic field vector is again in the vertical direction only, and this angle is going to be 90 minus theta. So the torque due to magnetic field is going to be M cross B, which in terms of magnitude is MB cos theta, right? Now M is I into A, which is I pi r squared, times B naught times sine 90 minus theta, which is cos theta. So this is the magnetic field torque, and the torque due to gravity is pretty simple. So the mg is acting at the midpoint of the rod, and the moment arm is actually L by 2 sine theta, right? So the torque due to gravity, so torque due to mg is going to be mg L by 2 sine theta, and both of them have to be equals at the equilibrium position, and the relation for theta that we obtain is this particular expression, which actually matches with option B, right? So in the question what they were intending to ask is the equilibrium angle theta, and which is probably what most people have answered in the paper, but the way they worded the problem is actually not correct. So what they should have asked is what is the angle turned by the loop by the time it reaches the equilibrium position, or something like that. But the thing is, what will happen is this ring will keep oscillating about the vertical position and the extreme position, okay, and it will keep oscillating back and forth, and you guys can also figure out the extreme angle theta right? This is the position when the ring actually comes to rest. You guys can confirm this yourself. All you have to do is conserve energy between the initial position and the final position, and you'll actually figure out this angle also turns out to be theta. Okay, so the in this case the max angle that is turned is actually 2 theta. Now guys, if they wanted the relation for the maximum angle turned by the loop, then the answer will be 2 theta. Now for a second, let's say alpha is that angle, so alpha is equal to 2 theta. Okay, so alpha by 2 is nothing but theta, guys. So if I take tan theta on both sides, I can say tan of alpha by 2 is 2 I pi r b naught divided by mg, exactly the same as this value. So this would have been the relation provided if the question was what was the maximum angle turned. Okay, then there would have been a by 2 here, but in no option there is a by 2. I mean, clearly they were intending to ask the equilibrium condition. There is a problem in which the question is worded, but other than that, this question is fine, I guess. I don't think this is going to be a bonus. Okay guys, so that was it for this video. We'll solve the rest of the problems in the upcoming videos. If you enjoyed the video, please do like, share and subscribe, and that's it. Thanks for watching.